The universe has a reputation for being calm, cold, predictable, a place where everything follows rules so clean you can write them down and trust them for centuries. But that is only true until you start looking closely. Then the sky turns into a crime scene full of clues that do not quite fit. A signal appears once and never returns. A star dims as if something huge passed in front, then refuses to repeat the pattern. Perfect circles glow in radio light where no perfect circles should exist. It is like the cosmos is daring us to explain it. Stay with me through this investigation, and if you enjoy these deep dives into the strange, please like and subscribe. We tend to think of science as a machine that turns questions into answers. Feed it data, crank the handle, out comes the truth. Sometimes that happens. A planet tugs on a star, the star wobbles. We discover a new world. A galaxy's light stretches redder and redder. We realize the universe is expanding, beautiful, clean. But the reason those stories feel satisfying is because we do not usually hear about the cases where the machine jams. Tonight is about those jams. Not rumors, not sci-fi, not the kind of speculation that floats around because it feels exciting. This is about real observations, real instruments, real signals, dips, rings, voids, cold spots, chemical fingerprints, and cosmic explosions that have been seen and measured. And in every case, the part that makes it strange is painfully simple. We cannot fully explain it yet. That word yet matters. Because the best way to misunderstand science is to imagine that not knowing is a failure. Not knowing is the front door. It is where the story starts. It is the moment the universe hands you a puzzle piece and refuses to show you the box art. And there is a reason puzzles like these are showing up more often now. The universe did not suddenly get weirder in the last few decades. We just got better at noticing how weird it always was. Our telescopes became more sensitive. Our surveys became wider. Our data became continuous instead of occasional snapshots. We started watching the sky the way a wildlife camera watches a forest, not just waiting for the perfect moment, but observing everything patiently for years. When you do that, you stop seeing the universe as a set of famous objects and start seeing it as a living system. And living systems always have outliers, always have odd behaviors, always have rare events that your neat categories did not expect. So the real question of this documentary is not just what these strange discoveries are, it is what they do to us. Because every time we find something that does not fit, we face a choice. We can ignore it, we can call it noise, we can say that it must be a mistake and move on. Or we can do the harder thing, we can admit that nature is under no obligation to match our expectations, and follow the evidence wherever it leads. That sounds noble. It is also psychologically brutal. Our brains love closure. If you show a person an incomplete pattern, their mind tries to complete it. If you show them a mystery, they want it solved quickly, cleanly, with a satisfying ending. Science rarely gives you that. Science gives you long stretches of uncertainty with occasional bursts of clarity. It gives you years of careful measuring, arguing, correcting, and remeasuring. It gives you situations where the correct answer is not a single sentence, but a whole new way of thinking. So when we meet a strange thing in space, we have to be careful about two equal and opposite mistakes. One mistake is to get bored, to assume that if there is no easy answer, it must not matter. That is how you miss revolutions before they happen. The other mistake is to get drunk on mystery, to treat every anomaly like a message, to see intention where there is only probability, to hear aliens in every static burst, to declare that physics is broken because one measurement feels uncomfortable. The real skill is balance. Curiosity with restraint, wonder with discipline, a willingness to say this is weird, paired with the humility to say we might be wrong about what we think we saw. That balance will guide us through everything we are about to explore. We are going to start with an event so famous that it has a nickname written in ink, a narrow, powerful radio signal detected for only 72 seconds, then lost forever to silence. We will move from that to a star whose light drops by an amount that makes planets look like gnats. Then we will step into radio space and find enormous perfect circles that do not show up in ordinary light at all. We will zoom out to structures so large that they challenge the comforting idea that the universe looks the same in every direction when you go big enough. Then we will do something that feels almost existential. We will stare into emptiness, into voids so wide they make you question what it means for matter to be spread out at all. And just when you think the weirdness is confined to distant galaxies, we will come back to our own neighbourhood. We will meet a star that seems to carry radioactive elements that should have vanished long ago. We will meet a visitor from interstellar space that behaved like nothing we had seen before. We will watch explosions that brighten and fade like cosmic flashbulbs. And we will end with a star whose age, at least on paper, gets uncomfortably close to the age of the universe itself. These are not just trivia. Each one is a pressure test, a stress fracture, a little crack where reality presses against our models. Sometimes a crack is just a crack, a measurement error, a selection effect, a rare but normal event that looks shocking because you're seeing it for the first time. But sometimes a crack is the start of something bigger, a hint that the model needs a patch or that we are missing a whole category of phenomena. If you want a mental image, think of our understanding of the universe like a map. Most of the map is labelled stars, galaxies, black holes, supernovae, expansion, background radiation. We know the roads, we know the rivers, we know where the mountains are supposed to be, but there are still blank regions marked with warnings, here be dragons, and every strange discovery we are about to explore is a dragon sighting. Sometimes the dragon turns out to be fog, sometimes it turns out to be a whale, and sometimes, very rarely, it turns out to be a new continent. So let us start where so many cosmic mysteries begin, with a human being staring at data, thinking it will be boring, and suddenly feeling their stomach drop as the universe does something that it should not do. Imagine spending your days listening to the universe the way you listen to a room at night. Mostly silence, some faint hiss, occasional pops you learn to ignore. That was the job in 1977 at the Big Ear Radio Telescope at Ohio State University. Part of a project called the Search for Extraterrestrial Intelligence, or SETI, which is exactly what it sounds like. Point an instrument at the sky, scan patiently, and hope that somewhere out there, something intelligent leaks a signal strong enough to notice. Most days, nothing happened. Then on August 15, 1977, a man named Jerry Eman was reviewing the printed data from the telescope and saw a sequence that looked wrong in the best possible way. The numbers jumped. The signal strength rose to about 30 times the normal background noise. It climbed, peaked, and fell in a smooth curve that matched what you would expect if a radio source drifted through the telescope's beam as Earth rotated. And in the margin of the printout, Eamon wrote a single word that became famous. Wow. The wow signal lasted about 72 seconds. Not an hour, not a night, 72 seconds. It arrived from a direction in the sky near the constellation Sagittarius, and the frequency was the detail that made people sit up straighter. It appeared close to 1,420 megahertz, near a natural emission frequency of neutral hydrogen. Hydrogen is the most common element in the universe. If you were an engineer trying to pick a cosmic calling card, you might choose a frequency tied to something everyone would understand, like carving a message on the most common stone. But here is the cruel trick. The Big Ear telescope had two receivers that scanned the same patch of sky a few minutes apart. The signal appeared in one receiver and not the other. That tells us the source was brief, less than a few minutes. Likely about what the printout suggests, roughly 72 seconds. So we have one clean spike, one direction, one frequency, one night, then nothing. That is the kind of thing that drives scientists insane, because it is the perfect shape of a discovery and the worst possible amount of evidence. One event is not a pattern. One event is a question mark. For almost 50 years, people have returned to that patch of sky with better instruments and sharper methods. They have listened on the same frequency and nearby frequencies. They have scanned and re-scanned. They have asked the obvious question again and again. Did it repeat? It did not. And the lack of repetition is not a side detail. It is the core of the haunting. Because if it was a deliberate transmission, why would it show up once and never again? If it was accidental, why did it land so precisely where you might choose to transmit? And if it was natural, what natural process makes a narrow band signal so clean that it looks engineered? Let us talk about that narrow band issue, because it is a big deal. Many natural radio sources in space produce emissions across a wider range of frequencies. Pulsars are broadband, supernova remnants are messy, even strange plasma processes tend to smear out. A narrow band signal is more consistent with a transmitter selecting a frequency, the way a radio station does. But consistent is not the same as proof. Earth-based interference can also be narrowband. A satellite, an aircraft, a ground transmitter reflecting off something, a piece of technology with a frequency that happens to sit near that hydrogen line by coincidence. So the first battlefield of the WOW signal is not aliens versus nature, it is space versus Earth. The Big Ear telescope was designed with a specific purpose, and part of that purpose was to reduce the chance that local interference would be mistaken for a cosmic signal. The signal also appeared to come from a fixed direction on the sky, rather than tracking with a known satellite path. But those details do not seal the case, they just keep it open. Then there is the comet hypothesis, one of the more famous natural attempts at closure. Comets can carry large clouds of hydrogen. The solar wind can interact with those clouds and produce radio emission. In 2016, Antonio Paris suggested that comets known as 266P Christensen and P2008Y2 were in that general region during the Mean 7 event. That sounds tempting. Hydrogen, line frequency, hydrogen cloud, comet passing through the right region. Done, except the details push back. The WOW signal was narrow. The comet explanation would need to produce emission concentrated in an unusually tight frequency range, and the Big Ear telescope could not pinpoint the source perfectly, which means the region of uncertainty is wide enough that multiple objects could be candidates. So the comet idea is possible, but it is not a satisfying lock. That is what makes the WOW signal so effective as a story. It is not that the alien explanation is strong, it is that every explanation we try carries a splinter, something that does not fit cleanly. If it was a spacecraft beacon, why one burst? If it was a lighthouse beam sweeping the sky, why did we never catch it again? If it was a one-time broadcast, why that frequency, why that direction, why that timing? If it was terrestrial, how did it slip past filters and look so sky-fixed? If it was natural, why did it mimic the signature of something artificial? Now here is the most honest thing we can say. The WOW signal is not proof of extraterrestrial intelligence. It is also not neatly solved. It is a real observation that remains unexplained. And as a scientific lesson, it teaches something sharp. Some mysteries are not hard because the universe is hiding. They are hard because the universe is brief. It gives you a glimpse and then moves on. 72 seconds. That is all we got. If the WOW signal happened today, we would likely do better. Modern arrays can pinpoint positions far more precisely. They can record more of the signal structure. They can coordinate follow-up rapidly. But 1977 was a different era. The data was literally on paper. The opportunity passed. And that is the uncomfortable truth at the heart of all anomaly hunting. Sometimes the universe hands you a one-time event, and you either catch enough detail or you do not. There is no redo button. So we keep the file open, we keep listening, we keep building instruments that can catch the next one. Because whether the WOW signal was an alien shout across the void, a rare natural burst we have not categorized, or a strange accident of human technology, it points to the same conclusion. There are things happening out there that we do not fully understand yet. And the next mystery takes that idea and turns it into something you can almost feel with your eyes. Not a sound in the radio. A star in visible light, quietly dimming as if something enormous is passing in front of it. If the WOW signal feels like a whisper you almost heard, Tabby star feels like watching a streetlight flicker while you are standing right under it. You can see it, you can measure it, you can replay it, and the more you look, the less comfortable that the explanations become. Tabby star is the nickname. It comes from astronomer Tabitha Boyajian, who led the early work that made the object famous. The star's official catalogue name is Kepler Input Catalogue 8462852. It sits at about 1,460 light-years away in the constellation Cygnus. In ordinary starlight, it looks like nothing special, slightly larger and hotter than our Sun, not the kind of star you would circle in red ink at first glance. Then the Kepler Space Telescope watched it. Kepler's main job was simple in concept and obsessive in practice. Stare at more than 100,000 stars and measure their brightness with ridiculous precision. The reason is that planets reveal themselves by stealing a tiny bit of light as they pass in front of their star from our viewpoint. For a sun like ours, an Earth-sized planet would dim the light by about 0.01%. Jupiter would dim it by about 1%. Those dips are small, clean, and repeat on a schedule. That is what a planet looks like in the data, a tiny heartbeat. Tabby's star did not give Kepler a heartbeat, it gave it a blackout. In 2011, the light from the star dropped by about 15%. That is not a planet. That's not even close. Then it came back as if nothing happened. Later, Kepler recorded an even deeper event, a dip of about 22%. Again, the star recovered. The dips were irregular. They did not repeat with a steady rhythm. They varied in depth and duration. Sometimes the star dimmed a little, sometimes it dimmed a lot. It was like watching a lighthouse, except the lighthouse was the thing going dark. At first, the mind reaches for something solid. A big planet, a brown dwarf, a companion star. But the math is ruthless. To block 22% of a star's light, you need an object or collection of objects with an enormous cross-section. A Jupiter-sized planet does not do it. A single object that big starts to sound like another star, but there is no evidence of a normal stellar companion doing a clean eclipse. And even if there were, the timing would repeat. So the story pivoted from simple to unsettling. A star is dimming in huge chunks, and the pattern refuses to behave like an orbiting world. This is where the alien megastructure idea entered the conversation, not as a conclusion, but as a kind of intellectual stress test. The idea traces back to physicist Freeman Dyson in 1960. Dyson asked a basic question. If a civilization becomes unimaginably advanced, what do they do about energy? One answer is that they might build a vast system of collectors around their star, not a solid shell, but a swarm of structures intercepting starlight and converting it into power. If you had a swarm like that, it could cause irregular dimming. Different pieces would block different amounts of light at different times. The dips could be deep, the timing could be strange. In other words, the data could look like Tabby's star. Now we have to be careful here, because there is a trap in the human brain. When a mystery is painful, a dramatic explanation can feel soothing. It gives you an ending. It makes the weirdness feel intentional. It turns an anomaly into a message. Most astronomers did not think Tabby's star was a megastructure, but the reason the idea took off is that the star forced people to say something rare in public science. We do not have a good explanation yet. So the work turned to natural causes, the kind that can produce chaos without intelligence. One early contender was a swarm of comets. Comets carry dust and gas, and a large family of them passing in front of the star could produce uneven dimming. But again, the numbers bite. You would need an enormous amount of material to block that much light. And comets carry dust that should change the colour of the star when it dims. Dust tends to scatter blue light more than red light, making the star look redder during dips. For a while, Tabby's star did not seem to show the expected colour change, which weakened the dust-heavy comet picture. Another contender was a catastrophic collision. Two large bodies smashed together near the star, and a debris cloud forms, spreading and clumping, drifting through our line of sight. That could create irregular dips, especially if the debris is structured. But this idea has its own signature. Warm dust should glow in infrared light. If there is a huge cloud of debris, you expect excess infrared radiation. Observations did not show the strong infrared excess that would make the collision story feel obvious. Then there is the possibility that the star itself is responsible. Stars can be variable. Some change brightness because their surfaces pulse, or because star spots rotate in and out of view. But Tabby star's behaviour did not match known classes of variable stars, and the dips were too deep and too oddly shaped. So the mystery persisted, and it did not go away quietly. In 2017, astronomers caught Tabby star dimming again and observed it across multiple wavelengths. This was a crucial moment because it lets the universe answer with physics instead of vibes. What they found was subtle but important. The dimming was stronger in blue light than in red light. That is what dust does. Small dust particles scatter blue light more effectively than red light. It is the same basic reason Earth's sky is blue. So this result nudged the story back toward a dust-based explanation. Not necessarily comets, not necessarily a single collision, but some kind of material around the star that can drift into our line of sight and selectively filter light. But even this does not fully settle it. Dust explains the colour dependence, but it raises other questions. Where is the dust coming from? Why is there so much of it? Why does it appear in such irregular and dramatic events? Why do we not see this behaviour in countless other stars Kepler monitored? So the tension changes shape. At first, the tension is about possibility. Could this be something extraordinary, something built? Then the tension becomes more grounded, and in some ways more disturbing. Because dust is ordinary, collisions are ordinary, comets are ordinary. The question becomes how ordinary processes can organize themselves into something this extreme, this rare, and this confusing. And that is the real theme of our whole journey. The universe does not always need new physics to surprise you. Sometimes it just needs a configuration you have never seen before. As of 2025, Tabby star remains one of the strangest well-observed stars in the sky. Not because the explanations are impossible, but because none of them feel complete. Something is blocking the light, the effect is real, the star keeps doing it, and the pattern keeps refusing to become comfortable. So we hold two ideas in our hands at the same time. The conservative one is that this is dust and debris in a complex orbiting environment we do not yet model well. The adventurous one is that nature has handed us an edge case that might point to a phenomenon we have not categorized. Either way, Tabby's star does something valuable. It forces us to admit that even in a sky full of familiar stars, some of them do not read the script we wrote for them. And now we take that lesson and push it into an even stranger direction, because the next anomaly is not a single star or a single signal, it is geometry itself, painted across intergalactic space. There is a particular kind of shape that makes astronomers suspicious. A circle, not because circles are impossible in nature, but because circles are what you get when the universe is kind to you. When an explosion is roughly symmetric, when a shell expands into space without getting shredded, when your viewing angle happens to line up just right, and when your data pipeline is not lying to you. So when modern radio surveys started finding enormous circles in the sky, not in visible light, not in infrared, only in radio, the first reaction was not awe, it was doubt. In 2013, researchers working with the Australian Square Kilometre Array Pathfinder, often shortened to ASCAP, were surveying the radio sky. ASCAP is designed to do something that older radio telescopes struggled with: cover large areas quickly while still being sensitive to faint, spread-out structures. It is the difference between shining a flashlight through a keyhole and turning on a stadium light. When the data came back, the team saw something that looked like a processing artifact. A ring, a nearly perfect circular ring, huge in apparent size, with nothing obvious in ordinary telescope images to match it. Then they found more. Then other instruments saw them too. And the uncomfortable truth settled in. The circles were real. They were given an honest name that sounds almost like a joke. Odd radio circles. People also call them by their initials, ORCs, but the full name captures the vibe better. They are odd. They are circles, and they show up in radio. Here is what makes them so strange. Each odd radio circle appears as a ring or shell of radio emission, often cleanly outlined like a bubble. Many of them have a galaxy sitting near the center, usually a large elliptical galaxy. In visible light, that central galaxy can look fairly normal. Not always perfectly quiet, not always perfectly active, but not screaming the kind of energy you would expect to draw a giant circle around itself. And the scale is absurd. These rings are not the size of a solar system. They are not the size of a star. They are not even the size of a typical galaxy. They can span hundreds of thousands of light years, and some estimates put the largest approaching around 1 million light years across. That is several times the diameter of the Milky Way. It is an intergalactic structure, a thing that belongs to the realm where galaxies interact, not where single stars explode. So the central question becomes painfully simple. What on earth makes a ring that big in radio light? Astronomy has seen circular shapes before, and the first step is always to try the familiar categories and see where they fail. Supernova remnants can look circular. When a star explodes, the shockwave expands outward and can create a radio shell. But supernova remnants are tiny compared to odd radio circles. They are usually measured in tens or maybe hundreds of light years, not hundreds of thousands. They also live inside galaxies like ours, embedded in gas that leaves additional fingerprints. Odd radio circles are too large and too distant for that explanation. Planetary nebulae also form shells, and they can be beautifully round. But planetary nebulae are the farewell breath of dying stars. Again, they are small on cosmic scales, and they are local to our galaxy. Odd radio circles are not local. Their scales and distances push them far outside that category. Then there are radio galaxies with jets. Some galaxies host actively feeding supermassive black holes at their centers. When matter falls in, the process can launch jets that punch outward and inflate large lobes of radio emission. In some cases, if you view those lobes from a certain angle, you can get structures that look vaguely circular or ring-like. So this is a serious contender, because it lives in the right neighbourhood of scale. But again, the details fight back. In many odd radio circle systems, the central galaxy does not look like a classic powerful radio galaxy. You do not always see the obvious jets or lobes you would expect. The radio ring can appear as a clean shell rather than two opposing lobes. It is as if the galaxy fired a spherical blast instead of a pair of beams. So what could cause a spherical blast on these scales? One idea is a gigantic shockwave. Picture a galaxy that goes through an extreme event, an outburst from its central black hole, or a furious episode of star formation, or both. Enormous energy is dumped into the surrounding gas. A shockwave propagates outward for millions of years, compressing magnetic fields and accelerating particles. Those energetic particles spiral in magnetic fields and emit radio waves, creating a glowing shell. That sounds promising because it explains why you would see a ring in radio but not necessarily in visible light. Radio emission can trace magnetic fields and energetic electrons even when the gas itself is faint. But this idea also raises the most annoying kind of question. If galaxies can do this, why do we not see it everywhere? Galaxies have active phases, black holes flare up, starbursts happen, mergers stir chaos. The universe has had billions of years to produce shells, yet odd radio circles appear rare. By 2025, only on the order of a dozen had been reported, even with surveys designed to find faint radio structures. So either the event that makes them is truly uncommon, or the conditions required are narrow, or we are missing many because they are hard to detect and we only just developed the right instruments. Another idea is that they are connected to galaxy mergers. When galaxies collide and merge, their gas can slam together, driving shockwaves on huge scales. Over time, this can create extended structures, and the merger can also wake up the central black hole, adding more energy to the system. A merger could plausibly create a large, roughly spherical disturbance that later shows up as a ring in radio. But again, mergers are common. The universe is basically a slow-motion demolition derby. So if mergers alone made odd radio circles, we would expect a sky full of them. Which brings us to an important psychological moment in every mystery story. Sometimes the universe is not hiding the mechanism, sometimes it is hiding the context. Odd radio circles might not be one thing. The label might be a bucket we made because we saw a similar shape. One circle might come from a black hole outburst. Another might come from a merger shock. Another might come from a different process entirely. The ring could be the shared symptom, not the shared cause. And that is exactly where the science still sits. We are in the discovery phase. We are still counting them, cataloguing them, comparing them, asking what the central galaxies have in common and what the surrounding environment looks like. Are these rings happening in clusters of galaxies or in quieter regions? Do the central galaxies show evidence of past activity even if they are calm today? Do the rings have faint counterparts in X-rays or optical emission, or are they radio-only ghosts? This is the kind of mystery that only appears when your instruments become good enough to reveal the faint architecture of the universe. For decades, these rings could have been there, but invisible to us. Not because they were secret, but because we were blind to that wavelength and that sensitivity. That is a humbling thought. The sky we see with our eyes is not the full sky. The universe is broadcasting in many channels at once, and only recently have we started to tune in properly. Odd radio circles are strange because they look like intentional geometry, drawn with a compass across intergalactic space. But the deeper strangeness is what they imply about our knowledge. We built a mental catalogue of what galaxies do, and then a better radio survey showed us a new kind of footprint. A footprint without a clear animal. And that is the pattern you should watch for as we continue. The more we observe, the more the universe reveals structures that sit just outside our existing categories, not far enough to be magic, but far enough to make us rewrite a few pages. Next, we zoom out even further, beyond individual galaxies, beyond rings, into the largest structures people claim to see in the cosmos. Structures so large they threaten one of the quiet assumptions that holds modern cosmology together. By the time we reach the scale of galaxies, the universe already feels enormous. A galaxy is not a place, it is a population. Hundreds of billions of stars drifting in a dark halo of mass we cannot see directly. stitched into the cosmic web like beads on invisible threads. So you would think that if anything in astronomy should feel stable, it would be the biggest picture, the zoomed-out view, the map where all the messy details blur into something simple. That hope has a name. It is called the cosmological principle. The idea is not that the universe is perfectly uniform. Clearly it is not. We have clusters and filaments and voids. The idea is that if you zoom out far enough, those lumpy details average away. On the largest scales, the universe should look roughly the same in every direction. Not identical, but statistically similar. Homogeneous and isotropic, as cosmologists like to say, meaning no special centre and no preferred directions when you step far enough back. This principle is not just poetic, it is one of the quiet beams holding up the standard model of cosmology. It is baked into how we interpret the cosmic microwave background. It is built into simulations of how structure forms. It is the assumption that lets us connect a universe that began almost smooth to the universe we see now, threaded with galaxies. Now imagine someone walks into the room and says, "I think we found structures so large they might not be allowed." Not as a metaphor, as a measurement. In 2021, and then again in 2024, astronomers reported two enormous features in the distribution of galaxies, both so large they challenge the usual intuition about what can grow within the age of the universe. One is called the Giant Arc, the other is called the Big Ring, and the details are what make it hard to shrug off. The Giant Arc was reported by Alexia Lopez, a doctoral researcher at the University of Central Lancashire. It is described as a curved arrangement of galaxies and galaxy clusters spanning about 3.3 billion light-years. That is not the distance to it. That is the size of the structure itself. Light would take 3.3 billion years to cross from one end of the arc to the other. Then in 2024, the same research team reported another structure in the same region of sky at a similar distance, a roughly circular arrangement called the Big Ring, about 1.3 billion light-years in diameter. Both of these features were reported at around 9.2 billion light-years away from us. So now the mind does what it always does. It asks the obvious question. If the universe is supposed to look smooth at large scales, why are there giant shapes, arcs and rings, spanning billions of light-years? Part of the tension comes from a rule of thumb that emerges from the standard picture of structure formation. Gravity has had a limited time to pull matter together since the Big Bang. That time limit implies a rough upper bound on how large coherent structures should be, often quoted around about 1.2 billion light-years. If that bound is roughly right, then a structure 3.3 billion light-years across is not just slightly awkward, it is dramatically awkward. It is the universe building a bridge longer than the materials should allow, and this is where scientific caution kicks in, because there is a second principle that is just as important as the cosmological one. Never underestimate the human brain's ability to see patterns in noise. If you take a cloud of points and stare at it long enough, you can draw a line through it. You can draw a curve, you can find a ring. It is what our minds do. We are meaning-making machines. We survived by recognizing patterns, not by calculating confidence intervals. So the first fight around claims like the Giant Arc and the Big Ring is not philosophical. It is statistical. Are these real structures, or are they chance alignments that look coherent because we are connecting dots? The team behind the Giant Arc attempted to quantify that. They reported that the probability of the arc being a random arrangement is about 1 in 6,000. That is not impossible, but it is low enough to raise eyebrows. They argued that the structure appears unlikely to be a mere coincidence. They also argued that the statistics for the Big Ring are even more compelling. And then comes the detail that makes coincidence feel even less comfortable. Both features are in the same part of the sky, at roughly the same distance. Two unusual patterns in the same neighbourhood does not prove coincidence, but it changes the vibe. It suggests a shared environment, a shared history, or at minimum a shared data set that might be revealing something about how we are measuring structure at that epoch of cosmic time. So what could explain shapes like these without breaking the cosmological principle in half? One idea reaches back to the early universe. Baryon acoustic oscillations. In the first hundreds of thousands of years after the Big Bang, the universe was a hot plasma where light and matter were tightly coupled. Pressure waves moved through that plasma like sound through air. When the universe cooled enough to become transparent, those waves froze into the distribution of matter, leaving a preferred scale. a subtle ripple in where galaxies are more likely to be found. We do observe that effect, it's one of the pillars of modern cosmology, but the reported scales of the giant arc and big ring do not neatly match the typical baryon acoustics scale. They're much larger, which makes this explanation feel like it can contribute to the story without finishing it. Another idea is more exotic: cosmic strings. Cosmic strings are hypothetical defects in space-time imagined in some early universe theories, like cracks that formed as the universe cooled and changed state. If such strings existed, they could in principle influence how matter clumps, guiding galaxies into long, coherent structures. The problem is that cosmic strings are still speculative. There is no direct evidence that they exist, and invoking them feels like reaching for a tool we are not sure is in the toolbox. Then there is the possibility that nothing is broken, we are simply misreading the map. Maybe these features are not single connected objects, but projections. Maybe the arc is built from smaller structures aligned along our line of sight. Maybe the ring is an artifact of how we slice the data. Maybe selection effects and survey boundaries nudge the pattern into existence. This is not cynicism, it is hygiene. In astronomy, you do not get to poke the thing you found. You get photons, and you get inference. That makes statistics and methodology part of the physical story. But suppose the features hold up. Suppose more surveys, more independent datasets, more analysis confirms that there really are coherent patterns on these scales. Then the cosmological principle does not necessarily die, but it becomes less comfortable. It would suggest that the universe might be lumpier on large scales than the simplest version of the principle implies, at least in some eras, or at least in some regions. It could mean our theoretical limits on structure growth need refinement. Not because gravity stopped working, but because the details of how matter assembled it might be richer than the cleanest models assume. And that is the part people often miss. An anomaly is not a demolition, it is a measurement that asks for an update. The Big Bang does not evaporate because we find a giant arc. The expansion does not stop because we find a ring, but our confidence in how well we understand the biggest picture might need to loosen its grip, which is exactly why these claims are controversial. Not because scientists are afraid of being wrong, but because the stakes are high in a very specific way. The larger the scale, the more foundational the assumptions. And this is where our story turns. Up until now, the mysteries have been strange objects or weird stars, odd signals, ghostly circles. Here, the mystery is the architecture itself. Is the universe as smooth as we think when we zoom out? Or are we staring at a cosmos that has larger patterns than our standard story predicted? Next, we swing hard in the other direction, from too much structure to too little, to one of the strangest regions of near emptiness we have ever mapped. There is a special kind of fear that comes from emptiness. Not the cozy emptiness of a quiet room, but the vast wrong emptiness where you are sure something should be there and it is not. Space is already mostly nothing, of course. Even inside galaxies, the distances between stars are enormous. But the universe still has a rhythm. Clumps of galaxies, filaments, clusters, patterns that repeat like weather systems on scales we can barely hold in our minds. Then you find a region that looks like the universe forgot to finish it. It is called the Boötes Void, named after the constellation where it appears in our sky. It was identified in the early 1980s, when astronomers were mapping the distribution of galaxies and noticing something that felt almost like a mistake. A huge volume of space, roughly 330 million light-years across, with far fewer galaxies than expected. This is not a small gap. 330 million light-years is more than 3,000 times the diameter of the Milky Way. If you tried to imagine travelling across it at the speed of light, you would still be travelling for hundreds of millions of years. It is a cosmic bubble, a chunk of the nearby universe where the usual glow of countless galaxies thins out into an unsettling quiet. And here is the number that makes people stop and stare. Based on the average density of galaxies, this region should contain on the order of 2,000 galaxies. Instead, surveys found only around 60, not 0. Not perfectly empty, but empty enough that the difference feels like a missing city on a map. You're looking at a place where the cosmic web has a hole. At first, even the discoverers did not want to believe it. When your survey shows a giant gap, the first suspicion is your own method. Maybe your instruments missed faint galaxies. Maybe dust in our own galaxy hid things behind it. Maybe you sampled unevenly. Maybe the void was an artifact. But follow-up observations confirmed it. The Boötes Void is real. So now we have to ask the central question. How does the universe make something that empty? To understand that, we have to talk about the cosmic web, because the universe does not arrange galaxies randomly like scattered sand. Over billions of years, gravity turns small differences into large structures. Regions that start slightly denser attract more matter and become denser. Regions that start slightly less dense lose matter to their surroundings and become emptier. This is the part that is both beautiful and disturbing. The early universe was astonishingly smooth. The cosmic microwave background shows tiny variations, but tiny is the key word. Those small variations were enough, given in time, to build everything we see: clusters, filaments, galaxies, stars, us. Computer simulations of this process are one of the quiet triumphs of cosmology. You start with a nearly uniform universe and a small amount of initial lumpiness. You let gravity do its slow work. Over time, filaments emerge. Dense nodes form. Voids open up between them like bubbles in rising dough. The cosmic web appears not because someone designed it, but because physics is consistent and time is patient. Voids are not rare, they are part of the standard picture. What makes the Boötes Void special is not that it exists, but that it is an extreme example, a giant case that pushes toward the edge of what our models comfortably allow. Most voids are tens of millions of light years across. That is already huge. The Boötes Void is hundreds of millions of light years across. It is one of the largest known voids in the nearby universe. So the void becomes a stress test. If our story of structure formation is right, voids can grow, but only so far. They expand as matter flows toward denser regions. But the universe has a finite age, and gravity has a finite amount of time to sculpt the distribution. A void this large tells us we are looking at a place where the initial conditions were unusually low in density, and where billions of years of gravitational evolution amplified that early deficit. In other words, this emptiness might be a fossil, a preserved imprint of something that began as a subtle underdensity and was stretched and deepened across cosmic time. There is another twist that makes the Boötes Void feel less like an absence and more like an experiment. The galaxies that do exist inside it can be weird. When a galaxy lives in a crowded region, it is constantly being bothered. Gravity tugs it. Nearby galaxies steal gas, compress gas, collide, merge, distort, trigger bursts of star formation, or strip the material away. A galaxy in a cluster lives in a loud neighborhood. A galaxy inside a giant void lives alone. Its nearest neighbor might be millions of light years away. That changes everything about its social life. It can hold on to its gas longer. It can evolve without frequent encounters. It can form stars on a different schedule. Some galaxies inside large voids show higher star formation than you might expect, or odd shapes that hint at a quieter, stranger history. Not because void galaxies are magical, but because their environment is so different. So the Boötes Void is not just an empty space on a map. It is a natural laboratory. It lets astronomers study how galaxies grow when the usual cosmic harassment is turned down. But the core question remains: why is this particular region so empty? The best answer we have returns to the beginning. The early universe likely contained random fluctuations that were seeded at extremely early times, commonly associated with quantum fluctuations stretched by a brief period of rapid expansion in the first tiny fraction of a second. The details of that story are deep and still studied, but the implication is simple. The initial lumpiness was not perfectly uniform. Some regions started a bit higher, some started a bit lower. Most of those differences were small, but probability has a long tail. Every so often you get an extreme. The Boötes Void may be the result of one of those extremes, a region that began with a larger underdensity than average, then spent billions of years losing matter to its surroundings. And here is the part that makes the void feel almost philosophical. If that is true, then this enormous emptiness we see today started as a tiny statistical accident in the infant universe. A slight shortage of matter in one region, almost invisible at first, amplified by time into a cosmic desert 330 million light-years across. The universe is like that. Small beginnings, huge consequences. When we look at the Boötes Void, we are not just seeing empty space, we are seeing the long memory of gravity. We are seeing how the universe turns whispers in its earliest moments into megastructures and mega-absences. And the void also sets us up for the next mystery, because there is another kind of emptiness that shows up not in the modern distribution of galaxies, but in the oldest light we can observe at all. A cold region in the cosmic microwave background that looks a little too cold and a little too large to ignore. There is a moment in cosmic history that is so important it acts like a photograph, not a picture of stars or galaxies, because those did not exist yet. A picture of the universe itself, when it was still young enough to be almost simple. That photograph is the cosmic microwave background, the faint microwave glow that fills the sky in every direction. The cosmic microwave background is ancient light. It comes from a time when the universe was about 380,000 years old. Before that, space was a hot soup of charged particles. Light could not travel far because it kept bouncing off free electrons, like headlights in thick fog. Then the universe cooled enough for electrons and protons to combine into neutral hydrogen. The fog cleared, light escaped, and those photons have been travelling ever since, stretched by the expansion of space until they now arrive as microwaves. When we map this glow, we find something astonishing. It is almost perfectly uniform. The temperature is about 2.7 Kelvin, just a few degrees above absolute zero, but it's not exactly uniform. There are tiny warm and cool patches, the faint fingerprints of the earliest density variations. Those small differences are the seeds that gravity later amplified into all the structure we see today. So in a very real sense, the cosmic microwave background is our oldest reliable evidence. It is not a theory, it is a map we can measure, and it tells us what the universe looked like before galaxies existed, which is why one specific feature has been nagging cosmologists for more than 2 decades. On the map, there is a region that looks too cold. It is called the Cold Spot, and it sits in the direction of the constellation Eridanus. It covers a surprisingly large area of the sky, roughly 10 degrees across in its widest dimension, with an oval shape that is often described as about 10 degrees by 5 degrees. That is huge on the sky. It is dozens of full moons laid side by side. And the temperature difference, while tiny in everyday terms, is large in cosmic microwave background terms. The cold spot is about 70 millionths of a degree cooler than the average. That does not sound dramatic until you remember that the normal variations in the cosmic microwave background are already extremely small. In that context, the cold spot stands out like a bruise on a nearly perfect surface. The central question is simple. Is it real? And if it is real, what made it? The cold spot was first noticed in the early 2000s as maps improved. Satellites like the Cosmic Background Explorer, the Wilkinson Microwave Anisotropy Probe, and later the Planck mission, measured the microwave sky with increasing precision. Each new map refined the details, and the cold spot did not vanish. It persisted. So the conversation shifted from maybe it is a glitch to if it is not a glitch, what is it? When scientists talk about anomalies like this, they reach for statistics first. A universe with random initial fluctuations will occasionally produce an unusually large cold region by chance. The question is how often. Estimates vary depending on the details of the analysis, but the cold spot is often framed as having a probability around a few percent under the simplest models. Around 2% is a commonly cited ballpark. 2% is awkward, is not impossible, is not even absurd, but it is rare enough to make you pause. If you ran 100 universes with similar rules and random initial conditions, you might expect a cold spot like this in only a handful of them. We only have one universe. That is the brutal part. We cannot rerun the experiment. We cannot press reset and see whether the feature repeats. We are stuck with a single cosmic data point, and we have to decide whether it is a meaningful clue or a statistical fluke that we will never be able to fully judge. But science does not freeze just because the universe does not offer replays. Instead, scientists look for physical mechanisms that could create a cold spot, and they ask whether those mechanisms match what we see. The leading natural candidate is something that sounds like a trick, but is actually a consequence of gravity and expansion working together. It is called the integrated Sachs-Wolf effect. Here is the idea in plain terms. As a photon travels through space, it passes through regions with different gravitational pull. When it falls into a gravitational well, it gains energy. When it climbs out, it loses energy. In a static universe, those gains and losses would cancel out. But our universe is expanding, and that changes the timing. While the photon is travelling, the gravitational landscape can evolve. Now picture a gigantic underdense region, a supervoid, lying between us and the surface where the cosmic microwave background photons originated. A photon enters the void and begins to climb out of a gravitational well that is weaker than average. But because the universe is expanding, the void can change while the photon is inside it. The net result can be a small energy loss for the photon, which shows up as a slightly colder temperature in the map. That is the dream explanation. A void causes the cold spot. And there is a reason the idea became popular. Astronomers have found evidence of a large underdensity in the direction of the cold spot, not necessarily as extreme as the Boötes Void, but still substantial, a region with fewer galaxies than average. So the pieces seem to line up, except the numbers fight back again. Calculations suggest that even a large void may not be enough to explain the full depth of the cold spot. The void can account for some of the cooling, but not all of it, unless the void is far larger or far emptier than observations comfortably support. So we get the familiar shape of an unsolved mystery, a plausible mechanism that helps, but does not finish the job. That is where the conversation gets dangerous, because when ordinary explanations strain, extraordinary ideas start to look tempting. One of the most famous extraordinary ideas is a collision in the early universe. In some inflationary models, our universe is one bubble among many, forming in a larger multiverse. If two such bubbles collided early on, the impact could leave a circular or oval imprint in the cosmic microwave background, a scar in the oldest light. It is a thrilling idea. It is also speculative. The cold spot alone is not strong evidence for a multiverse collision, and there is no independent confirmation of such collisions, but the fact that scientists even discuss it tells you something about how stubborn the cold spot has been. Another possibility is the least romantic and the most likely in the long run. It might just be chance. 2% events happen. Rare does not mean impossible. Sometimes the universe rolls an unlikely number, and that is that. And because we only have one sky to measure, we may never be able to say with absolute confidence whether the cold spot is a meaningful anomaly or a statistical accident. But even that answer has power, because it teaches a key lesson about how cosmology works. At the largest scales, you do not get laboratory control. You get one universe and a lot of math. As of 235, the cold spot remains unresolved. It has not disappeared. It has not been cleanly explained. It sits there on the map as a reminder that even our oldest evidence contains surprises, and it connects directly to the theme of this entire documentary. Sometimes the universe challenges us not with a blazing explosion or a bizarre star, but with a subtle mismatch in a dataset we thought was our firmest ground. Next, we return from ancient light to modern starlight, to a star that seems to carry radioactive elements that should have been gone long ago, like finding fresh footprints in a desert that has not seen rain in 1,000,000 years. Some mysteries feel like they belong far away, at the edge of the observable universe. This one lives in a much more intimate place, a single star close enough in cosmic terms that it feels almost like a neighbour, and yet it carries a signature that should be impossible to keep. The star is called Przybylski's star. It sits about 370 light-years from Earth in the constellation Centaurus. From a distance it looks like a normal A-type star, meaning it is hotter and more massive than the Sun, bright and crisp and apparently ordinary. But when astronomers spread its light into a spectrum and read the dark absorption lines like a barcode, the star stops being ordinary and starts becoming a riddle. Because Przybylski's star appears to contain elements that should not be there. Not just rare elements, not just heavy elements, radioactive elements with short lifetimes, the kind that decay away on a timescale that is tiny compared to the age of a mature star. The most famous is technetium, an element with no stable isotopes. It is the kind of thing you do not expect to see sitting calmly in a star's atmosphere for billions of years. Yet lines associated with technetium have been reported in the star's spectrum for decades. Alongside it, promethium, another element that should not be able to stick around for long on cosmic clocks. To understand why that is such a shock, it helps to remember what a star is doing all day, every day. Stars shine because their cores fuse lighter elements into heavier ones, converting a little bit of mass into energy. In a star like the Sun, hydrogen fuses into helium. In more massive stars, helium can fuse into carbon and oxygen. In the most massive stars, the chain continues, building elements up to iron. Elements heavier than iron are generally associated with even more violent environments, like supernova explosions or other extreme events, where the physics allows rapid neutron capture and other processes to build the heavy end of the periodic table. Then those heavy elements get scattered. They drift into interstellar clouds. New stars form from that enriched material, inheriting some of the heavy stuff from previous generations. That is how a young star can contain iron, gold, uranium, and all the other ingredients the early universe did not start with. So far, so normal. The problem is radioactivity. Some heavy elements are radioactive but long-lived. Uranium has a half-life long enough that some of it can still exist billions of years after it formed. That is why you can find uranium on Earth today, but technetium is different. It has no stable form. The longest-lived isotope often discussed, technetium-98, has a half-life of about 4.2 million years. 4.2 million years is a long time for a human civilization. It is almost nothing for a star. A star like Przybylski's star is not 4 million years old, it is likely hundreds or thousands of times older than that. So if the star formed with technetium mixed into its atmosphere, that technetium should have decayed away long ago. It should be gone. Seeing it now is like finding fresh ice in the middle of a desert at noon. So where could it come from? The first class of explanations tries to keep the story inside normal physics by saying the technetium is being made now, not inherited long ago. But that is hard. The outer atmosphere of a star is not a particle accelerator. The temperatures and densities there are not the kind that naturally manufacture technetium through standard fusion. Stars do create heavy elements in certain late evolutionary phases, and some stars called asymptotic giant branch stars can dredge up freshly made material that includes technetium, which is a famous case in stellar astrophysics. But Przybylski's star does not fit neatly into that category. It is not the kind of swollen, late-stage giant where technetium is expected as a sign of ongoing nucleosynthesis and mixing. So the next idea is transport. Maybe the technetium is made deeper inside and currents bring it up. Again, the details resist. The interior conditions and structure of this kind of star do not obviously support a steady production of technetium, followed by efficient delivery to the surface in a way that keeps replenishing it at just the right rate. Then there is the most dramatic possibility, the one that feels like science fiction but has a real theoretical backbone, the island of stability. In nuclear physics, there is a long-running idea that far beyond the known elements, there might exist super-heavy nuclei that are not instantly doomed, but relatively long-lived. Not eternal, but stable enough to persist for meaningful spans of time. If such super-heavy elements exist in nature, and if they were present inside a star, their slow decay chains could produce intermediate radioactive elements along the way, potentially including technetium and promethium. In that story, Przybylski's star is not making technetium the normal way. It is leaking it as a byproduct of something even stranger, exotic super-heavy nuclei that we have never directly observed in the wild. It is a bold idea. It is also speculative. We have created some super-heavy elements in laboratories, but they usually decay very quickly. The island of stability remains more map than territory. Still, Przybylski's star is one of the reasons the idea keeps a pulse. When the universe shows you a signature you cannot explain, you start checking even the weird draws. There is another part of this star's personality that deepens the mystery. Its spectrum shows unusually strong lines of rare earth elements, things like holmium, dysprosium, and europium, at abundances that are extreme compared to the Sun. This places the star in a category called chemically peculiar stars. Chemically peculiar stars are not random mistakes. They are often understood as the result of atmospheric sorting. Radiation pressure can push some elements up, gravity can pull others down, magnetic fields can trap and channel plasma. Over time, the atmosphere can become stratified, concentrating certain elements in visible layers where they imprint strong spectral lines. That can explain why a star looks overloaded with some exotic ingredients. But even among chemically peculiar stars, Przybylski's star stands out. The combination of extreme rare earth signatures and short-lived radioactive candidates is not a routine pattern. It is like the star is a museum of strange chemistry, except the exhibits keep renewing themselves. Another practical idea is contamination from a hidden companion. If the star had a close neighbour like a white dwarf or the neutron star, and if material were being exchanged or accreted, that could in principle seed unusual elements. But evidence for such a companion has not been clear. Without an obvious orbital wobble or other telltale signals, the companion story remains uncertain. So we end up in the familiar place again. A real observation that does not fold neatly into our models. And this is what makes Przybylski's star such a powerful entry in our list of cosmic weirdness. It is not flashy, it does not explode, it does not shout in radio, it just sits there, shining steadily, while its spectrum whispers that something about its chemistry, its physics, or our interpretation is incomplete. Maybe the answer is mundane, buried in subtle line blending, atmospheric modelling, or the way magnetic fields sculpt a star's outer layers. Maybe it is a rare evolutionary phase we have not fully characterised. Or maybe the star was pointing at something deeper in nuclear physics, some pathway or reservoir we have not properly accounted for. Either way, the star teaches the same lesson as the cold spot and the Boötes Void. The universe does not need to break the rules loudly to challenge us. Sometimes it challenges us with a detail so small it lives in a thin line of dark ink inside a spectrum. And now, from a star with impossible chemistry, we turn to a visitor with impossible behaviour. Something that entered our solar system from the dark between stars gave us only a brief window to study it, and left us arguing about what we actually saw. On October 19, 2017, astronomers using a survey telescope in Hawaii noticed a faint point of light moving against the background stars. At first, it looked like a familiar story. Another small body passing through the solar system. An asteroid, maybe a comet, something we could label and file away. Then the orbit came into focus, and the label started to fail. This object was not bound to the Sun. It was on a hyperbolic path, meaning it came from interstellar space and would leave again, never to return. It had approached from the direction of the constellation Lyra, dipped through the inner solar system, and was already on its way out when we truly realised what it was. The first confirmed interstellar visitor ever seen passing through our neighbourhood. It was named Oumuamua, a Hawaiian word often translated as scout or messenger, which sounds poetic until you remember what a messenger really is. A thing that arrives briefly, delivers a hint, and disappears before you can ask follow-up questions. And we had very little time. We only had weeks to study Oumuamua before it grew too faint. That forced astronomers into a strange sprint. Gather as much data as possible, fast, while the object raced away. And the data we did get was enough to create one of the most famous modern arguments in astronomy. Because Oumuamua behaved wrong. The first weirdness was its shape, inferred from how its brightness changed as it tumbled. The object brightened and dimmed dramatically, suggesting it was highly elongated or extremely flattened, presenting very different cross-sections as it rotated. Early estimates suggested something like 400 metres long and 40 metres wide, roughly a 10-to-1 ratio, a shape closer to a cigar than a potato. Later interpretations suggested a different geometry could fit. A pancake-like body, thin but wide, can also produce large brightness variations depending on how it tumbles. The details are hard because we never resolved it as an image. It was always a point of light. We were reconstructing a three-dimensional object from a flickering dot, but either way, it did not look like the typical small bodies we know. The second weirdness was what it did not do. Comets are famous for growing a coma, a cloud of gas and dust when they approach the sun. Sunlight warms their ices, the ices vaporize, and the escaping gas drags dust outward, creating that ghostly halo and tail. Even modest comets can show obvious activity when they get close enough. Oumuamua passed close to the sun, even inside the orbit of Mercury, and yet it showed no clear coma, no obvious tail, no visible outgassing plume. It looks more like an asteroid. And if it were just an oddly shaped asteroid, the story would still be interesting, but manageable. Then came the third weirdness, the one that turned the debate into a fire. After it passed the sun and headed back outward, Oumuamua accelerated slightly more than gravity alone predicted. When we track an object's motion through the solar system, we account for the gravitational pull of the sun and the planets. Those forces are well understood. They let us predict where the object should be, and when. Oumuamua was not exactly where the gravity-only model said it should be. It was being nudged. Now, comets get nudged all the time. Outgassing creates a small rocket effect. Gas jets act like tiny thrusters. That produces what astronomers call non-gravitational acceleration, and it is normal. But Oumuamua did not look like a comet. So we end up with an object that looks like an asteroid, but moves a little like a comet. That contradiction is the whole mystery. The first attempt at resolution was to keep it within the comet family, while explaining why we did not see the usual signs. Maybe it was outgassing in a way that produced little or no dust, so the coma was too faint to detect. Maybe the gas was something transparent or difficult to observe. Maybe it vented in a narrow jet that created thrust without creating a visible halo. This idea has a certain appeal because it uses known physics. It says the object is natural, and the missing coma is a detection problem, not a new category of reality. But it also raises questions. If outgassing was strong enough to create the observed acceleration, why was the object not spinning up dramatically from uneven thrust? Why did we not see clearer chemical signatures? And what kind of material outgasses efficiently without producing the dust that usually comes along for the ride? So another idea entered the room, one that sounds gentle but leads to wild conclusions. Sunlight itself can push. All objects feel radiation pressure because photons carry momentum. For most asteroids, that push is tiny compared to gravity. But if an object is extremely thin and light, like a sheet, radiation pressure can become significant enough to measurably alter its path. In other words, if Oumuamua were something like a sail, sunlight could explain the extra acceleration without outgassing. This is where the story gets controversial because once you say sail, the mind jumps. In 2018, Harvard astronomers Avi Loeb and Shmuel Bayali argued that the radiation pressure explanation points toward a thin, possibly reflective object, and they raised the possibility that it could be artificial. Not a guaranteed alien craft, not a confident declaration, but a proposal that the data should at least allow the question. Most astronomers pushed back hard, and for good reason. The alien hypothesis in astronomy is a last resort. Not because aliens are impossible, but because the space of natural explanations is vast. And history is full of cases where something weird became normal once we understood it better. Pulsars were once jokingly called little green men because their signals were so regular. They turned out to be neutron stars. Oumuamua sits in that same psychological zone. It is weird enough that it tempts dramatic stories, but the evidence is not strong enough to demand them. It is an ambiguity machine. And the cruelest part is that the object left before we could interrogate it properly. It is gone, too distant and too faint to study now. We have only the brief window of data from those few weeks, and the debates that followed. If you want to feel the shape of the problem, compare it to the WOW signal. That was 72 seconds of radio. Oumuamua was weeks of optical data. That is better, but still not enough. We did not get a close-up. We did not get a spectrum rich enough to settle the outgassing question cleanly. We did not get a second chance. Then in 2019 we got something that should have made the argument easier, but instead made Oumuamua even stranger by contrast. Another interstellar object was discovered, named 2I Borisov, and Borisov behaved like a normal comet. It had a coma, it had a tail, it outgassed like the comets we already know. It was interstellar, yes, but it was not confusing. Oumuamua remained unique. So what is the most honest conclusion? Oumuamua was the first confirmed interstellar visitor, and it did not fit neatly into our existing categories. It was shaped oddly. It showed no obvious coma. It experienced non-gravitational acceleration. Natural explanations exist, but none feels perfectly satisfying to everyone. Artificial explanations are possible in principle, but not required by the evidence, and they carry extra assumptions that science tries to avoid unless forced. In a way, the most important lesson is not what Oumuamua was. It is what Oumuamua did to our readiness. It reminded us that the solar system is not sealed. The galaxy is full of debris ejected from other star systems. Some of that debris passes through our neighborhood. We can detect it now. We can build better surveys to catch the next one earlier. We can plan rapid response observations across many wavelengths. We can treat the next interstellar visitor not as a surprise, but as a target. Because the next one might be mundane like Borisov. Or it might be another Oumuamua, another object that refuses to behave. And in the next part, we look at a different kind of refusal. Not a visitor passing through. An explosion flaring in a distant galaxy so bright and so fast that it forces astronomers to admit they may have missed an entire category of cosmic death. In June 2018, telescopes watching the sky for transient events saw something ignite in a galaxy about 200 million light-years away. At first, it looked like a supernova, because that is what you expect when a new point of light suddenly appears where there was none. Stars die, they explode, we catch them, we catalogue them, the universe keeps rolling. Then the brightness kept climbing and it climbed too fast. This event was labelled at 2018 COW, a name that came from an automated system that assigns us letters almost at random. But the nickname stuck because it felt absurdly casual for something so extreme. The COW was not just bright, it was shockingly bright. Estimates put it around 10 to 100 times brighter than a typical supernova at its peak, and it reached that peak in days, not weeks. That speed is the first reason it was so unsettling. Most supernovae take time. The star's outer layers expand, cool, and radiate. The light curve rises and falls with a rhythm that astronomers have come to recognize. The COW did not follow the rhythm. It was like someone flicked on a cosmic floodlight, held it there briefly, and then flicked it off again. It also faded quickly, in weeks, not months. So now we have a paradox that feels almost physical. How do you dump that much energy into visible light so quickly and then stop? When astronomers spread the COW's light into a spectrum, the weirdness deepened. The temperatures inferred were extremely high, with a strong blue and ultraviolet component, and the spectral features did not match the familiar templates for standard supernova types. The event seemed to involve material moving outward at very high velocities, in some interpretations a substantial fraction of the speed of light. Everything about it felt compact, violent, and impatient. And that is when the story turned from one weird event to a new category. Because once you have one COW, you start looking for more cattle. Astronomers searched archival data and monitored new surveys. There they found other fast, luminous transients with similar behaviour. Not identical, because nature rarely repeats itself perfectly, but similar enough to suggest a family. These became known as fast blue optical transients, a name that is almost painfully descriptive. Fast because they rise and fall quickly. Blue because their light is hot and shifted toward the shorter wavelengths. Optical because we see them in visible light. Transients because they appear and vanish. By 2025, only a modest number had been identified, on the order of dozens, not thousands. They're either rare or hard to catch, or both. And every explanation for them has to wrestle with the same core facts. Extreme brightness, rapid evolution, very hot emission early on, and spectral behaviour that does not sit comfortably inside our usual boxes. So what could cause something like this? One cluster of ideas says we are watching the birth of a compact object under unusual conditions. When a massive star dies, its core collapses. Sometimes it becomes a neutron star, an object so dense that a teaspoon of its material would outweigh mountains. Sometimes it becomes a black hole, a region where gravity becomes so intense that not even light escapes once it crosses the boundary. In a normal supernova, the collapse triggers an explosion that unbinds the star's outer layers. A lot of energy goes into kinetic motion, and the light emerges as the expanding debris glows. But suppose the explosion is not normal. Suppose the core collapse makes a newly born black hole or a rapidly spinning neutron star that dumps energy into the debris in an unusually concentrated way. A central engine, in other words. If that engine drives a jet or powers an intense shock that breaks out quickly, it could create a bright flash that peaks fast and fades fast. That is attractive because it gives you a mechanism that can be both intense and brief, but it also raises questions about the environment. A bright transient needs something to radiate. It needs material to convert energy into light. And the COW seemed to involve a complex interplay of fast outflow and surrounding matter. Another cluster of ideas points to tidal disruption. A tidal disruption event happens when a star wanders too close to a black hole. The black hole's gravity pulls harder on the near side than the far side, stretching the star and ultimately tearing it apart. The stellar material forms a stream, some of it falling into the black hole, releasing huge amounts of energy. Tidal disruption events are real and observed, and they can be extremely bright. The challenge is timing. Many tidal disruption events evolve over months, not days. The COW and its cousins are far faster. That does not kill the idea, but it forces a more specific version. Perhaps the black hole is lower mass. Perhaps the disrupted object is not a normal star, but a compact star like a white dwarf. Perhaps the geometry and the fallback of debris create a rapid, efficient conversion of energy into visible light. It is a plausible path, but the parameter space is tricky, and the observations do not yet point to one clean answer. A third cluster of ideas involves collisions between compact objects. White dwarfs can collide, neutron stars can merge, a neutron star might collide with a white dwarf. These are violent events that can release enormous energy quickly. We already know neutron star mergers can produce bright transients and heavy elements because we have seen them in both gravitational waves and light. But the cow-like events do not perfectly match the known signatures of those mergers. The timescales and spectra differ in ways that keep the category open. What makes this family of events so important is not just the fireworks. It is what they imply about our blind spots. For a long time, astronomers built their understanding of stellar death around events that are relatively easy to catch. Supernovae that rise over weeks and fade over months are visible long enough that even a slow survey can notice them. Fast events are much harder. If something peaks in a few days and fades in weeks, you can miss it simply by looking away at the wrong time. The universe can be loud and still slip past you if it speaks too quickly. Modern surveys change that. Wide-field telescopes now scan large portions of the sky repeatedly. Automated pipelines flag new points of light. Follow-up instruments pounce. That is how the cow was caught, and it is why the category exists at all. It is not that these events were not happening before, it is that we were not watching in the right way. This should make you slightly uneasy, in a productive way, because it means the cosmos may contain entire classes of phenomena that are not rare in reality, only rare in our datasets. Events that are short-lived, events that are faint, events that hide in wavelengths we did not monitor well. The cow is not just an anomaly. It is a warning that our catalogue of the universe is biased by our attention span. As of 2025, fast blue optical transients remain one of the most active puzzle boxes in time-domain astronomy. Each new detection adds constraints. Some show signs of dense surrounding material, suggesting a star that shed a lot of mass shortly before it died. Some show evidence of a persistent central source, hinting at an engine rather than a simple explosion. Some resist both stories, and that is exactly what you would expect at the birth of a new category. First you name it, then you discover it is not one thing, then you split it into sub-families. Then you finally understand which mechanisms produce which outcomes. We are early in that process, but even early, the cow and its relatives have already done something valuable. They have reminded astronomers that the universe does not only evolve on comfortable human timescales, some of its most revealing events are over almost as soon as you notice them. Next, we meet a star that creates a different kind of discomfort. Not an explosion that dies too fast, but a star that seems too old enough to press against the age of the universe itself and make our measurements squirm. Some mysteries explode, some whisper in radio, some hide in rings of faint emission. This one just sits there, shining steadily, and quietly challenges the most basic number in modern cosmology. How old is the universe? We think we know. Multiple independent measurements point to an age of about 13.8 billion years. That number is not a casual guess. It's woven from the cosmic microwave background, the expansion history of space, and the ages of the oldest stellar populations we can study. It is one of the anchor points of our current picture. So what happens when a single star seems to come back with an age that brushes right up against that anchor, or even appears to lean past it? That star is often called the Methuselah star. Its catalogue name is HD 140283. It lies roughly 190 light-years away in the constellation Libra. You can see it with binoculars if you know where to look. It is not a hidden monster at the edge of the observable universe. It is nearby, familiar, in the way a distant star can be familiar. And yet its properties suggest it formed very early, when the universe was still young and chemically simple. The reason astronomers take its age seriously is that it carries the marks of being ancient. One of the strongest marks is metallicity. In astronomy, metals means every element heavier than helium. The early universe began with mostly hydrogen and helium, with only trace amounts of lithium. Everything heavier was forged later inside stars and scattered by supernovae and other violent events. Over time, the gas between stars becomes enriched. New generations of stars form with more metals mixed in. So a star with extremely low metal content is usually a star that formed early, before the universe had many chances to enrich itself. The Methuselah star fits that pattern. Its iron abundance is far below the Sun's, often described as hundreds of times lower. That makes it a member of the old population of the Milky Way, a survivor from the early era when galaxies were still assembling and heavy elements were scarce. But low metals alone do not give you a precise age. To estimate how old a star is, astronomers combine several measurements and feed them into models of stellar evolution. They measure the star's temperature, its luminosity, its composition, and they compare it to theoretical predictions for how stars change over time as they burn fuel and shift off the main sequence. The Methuselah star is a subgiant. That matters. It has used up the hydrogen in its core and is starting to evolve. Subgiants are valuable because their position on the Hertzsprung-Russell diagram is sensitive to age. Small differences in brightness and temperature can translate into significant differences in the time the star has been burning. So in principle, you can read the star like a clock. In practice, this is where the universe leans in and smirks. When astronomers applied these methods, they got a result around 14 billion years, with uncertainties that overlap the age of the universe. Depending on the exact inputs and model assumptions, the best fit value could land uncomfortably high, while the error bars still allowed a value just barely younger than the universe, something like 13.7 or 13.8 billion years. That is not a clean contradiction. It is worse. It is a tension, because the age of the universe is not a fuzzy number anymore. It has gotten tighter over the years. So when a star's age estimate presses against it, the likely conclusion is not that the universe is secretly older. The likely conclusion is that something in the star's age estimate is slightly off, or that the models still have subtle issues when they are pushed into extreme low metallicity territory. But here is why the star remains famous. Even as measurements improved, the discomfort did not fully go away. Part of the age estimate depends on distance. If you misjudge how far away the star is, you misjudge its true luminosity, and that affects the inferred age. Distance can be measured through parallax, the tiny apparent shift of a star's position as Earth moves around the Sun. Space missions like Gaia have made parallax measurements incredibly precise, improving distance estimates for vast numbers of stars, including this one. Another part depends on composition, and not just iron. Elements like oxygen affect the star's opacity, which affects how energy moves through it, which affects how the star evolves. Subtle shifts in inferred abundance can change the age you derive. That means the age estimate is not a single direct measurement. It is a chain. Temperature, luminosity, distance, chemical composition, model assumptions, and all the uncertainties combine. When you add uncertainties, sometimes the combined result lands on the edge of what is physically allowed. That is one reason the Methuselah star is not really a claim that the star is older than the universe. It is a reminder that precision can expose the cracks in our confidence. The star is telling us that our models are strong but not perfect, and our measurements are excellent but not absolute. There is another subtle reason the tension feels so sharp. The earliest stars in the universe were likely very different from what we see today. The first generation formed from almost pure hydrogen and helium, and may have been very massive and short-lived. A star like the Methuselah star, which contains some heavy elements, likely formed after at least one earlier generation had already lived and died, enriching the gas. That implies a short but non-zero delay after the Big Bang, perhaps hundreds of millions of years, before a star like this could form. So even in the most generous scenario, there is a ceiling on how old such a star can be. Not older than the universe, and not formed instantly at time zero. That ceiling makes any age estimate near 14 billion years feel like it is leaning into a wall. So what are the options? One option is that the star is at the low end of its uncertainty range, comfortably younger than the universe, and we are simply seeing the effect of combined measurement and modelling uncertainties nudging the best fit upward. Statistics can do that. The best fit is not the truth, it is the peak of a probability landscape. Another option is that our models of stellar evolution, while extremely successful, still have small systematic errors for very old, very metal-poor subgiants. Low metallicity changes how stars transport energy. It changes their internal structure. It changes how their ages map onto observable properties. If the models are slightly off in this regime, the derived ages can drift. A third option is that one of the key measurements, distance, temperature, or elemental abundances, has a subtle bias that is hard to notice because everything else looks consistent. The honest answer, as of 25, is that the Methuselah star remains uncomfortably old on paper, even though it cannot truly be older than the universe. The tension has eased in some analyses as measurements improved, but the star still serves as a famous example of how a single object can press on the edges of our framework. And that is the deeper value of the mystery. The universe does not only challenge us with the unknown, sometimes it challenges us with the almost misknown. A star that is so well studied, so nearby, so apparently ordinary, that it becomes a measuring stick for the cosmos. And when that measuring stick seems to bend, it is not the star asking for drama, it is the star asking for humility. Next, we step back and notice something that has been hiding in plain sight across all these cases. These mysteries look unrelated, but they may share a common lesson about how scientific revolutions begin. By now, your brain is probably doing what every good brain does when it gets handed a pile of mysteries. It starts trying to connect them. A one-time radio signal, a star dimming like something huge keeps drifting in front of it. Perfect rings you only see in radio light. Structures so large they make cosmologists argue about the smoothness of the universe. A void so empty it feels like a missing chapter. A cold patch in the oldest light we can see. A star with radioactive elements that should have decayed away. An interstellar visitor that acted like an asteroid and a comet at the same time. Explosions that rise and fade too fast. A star that seems uncomfortably close to the age of the universe itself. It is tempting to believe they are all symptoms of one hidden cause, one deep rule we have not discovered yet, one secret that would snap everything into place. And sometimes, in the history of science, that is exactly what happens. But sometimes the universe does something more mischievous. Sometimes it hands you a mix of unrelated puzzles that all share one theme. Not a single explanation, but a single lesson. The central question in this part is not what any one mystery is. It is what it means that we are finding so many of them at once, because the universe did not suddenly become stranger, we just got better at noticing. Think about how each of these mysteries entered our lives. The wow signal was detected because we built radio telescopes and started listening to the sky in frequencies our eyes will never see. Tabby's star was discovered because a space telescope stared at one patch of sky for years, measuring brightness changes so small and so consistent that irregular chaos stood out like a stain. Odd radio circles appeared when surveys became sensitive enough to detect faint, extended structures in the radio sky. The giant arc and the big ring were noticed through massive galaxy catalogues and statistical analysis that only became possible with modern data. The Boötes Void emerged when astronomers started mapping the large-scale distribution of galaxies instead of studying them one by one. The cold spot stood out when the cosmic microwave background was mapped with enough precision to turn the whole sky into a dataset. Oumuamua was found because automated surveys started scanning for moving objects at scale. The cow was caught because wide-field time domain astronomy began watching the sky like a security camera, always on, always checking. This is the pattern. Each mystery is a frontier effect. A thing that was always there, but invisible until we built the right tool, asked the right question, or watched long enough. And that leads to a deeply useful idea. These mysteries might not be connected physically, but they are connected epistemologically, meaning connected through how we know things. They are connected through the limits of our instruments and the assumptions in our models. The universe is not a single story, it is a library. If you only read one shelf, you will think all books look the same. Then you walk to another shelf and suddenly there are genres you did not know existed. Radio astronomy did that. So did X-ray astronomy. So did infrared astronomy. So did gravitational wave astronomy. Every time we open a new window, we find phenomena that do not fit neatly into our old categories. Not because the old categories were foolish, but because they were incomplete. Now here is where it gets even more interesting. Scientific revolutions often begin with a cluster of annoyances, not annoyances like people arguing online, annoyances like measurements that refuse to match theory. In the late 19th century, physics had a handful of such irritations. The orbit of Mercury did not match predictions perfectly. The speed of light behaved strangely. These looked like separate problems until a new framework linked them. Relativity was not invented to be dramatic. It was invented because reality would not stop disagreeing politely. Astronomy has lived through this cycle many times. Quasars looked like stars and behaved like nothing we understood until the idea of supermassive black holes at galactic centers turned the confusion into a mechanism. The accelerating expansion of the universe sounded like a mistake until the evidence became overwhelming and cosmologists had to admit something like dark energy was acting on the largest scales. In each case, the story begins the same way. We find something real that does not fit, then we try to force it into an existing box, then the box breaks. Then we either build a new box or we realize there was always a bigger box we were ignoring. So when you see a list of modern cosmic anomalies, you should not jump straight to one grand hidden truth. You should ask two more careful questions. First, are these anomalies truly unexplained, or are they partly explained but emotionally unsatisfying? Tabby star is a good example. The leading explanation now leans toward dust. That is a real physical mechanism with real observational support. The remaining weirdness is about details like where the dust comes from and why the pattern is so extreme. That is not a total mystery. It is a partial mystery. The cold spot is similar. A large void might explain some of it, but maybe not all. It could still be chance. It could still be subtle physics. It is unresolved but not lawless. Second, are we seeing new physics, or are we seeing new astrophysics? New physics would mean the underlying rules change. New astrophysics would mean the rules stay the same, but the universe is using them in ways we have not catalogued yet. Most of the time, new astrophysics wins. Pulsars were not new physics, they were new objects. Neutron stars were predicted, but nobody had seen the signature until radio telescopes revealed it. Quasars were not new physics, they were black holes eating. Even the weirdest explosions often turn out to be familiar ingredients arranged in unfamiliar ways, dense surrounding material, jets, magnetic engines, mergers. That does not mean new physics never happens, it means you have to earn it. And earning it requires the most boring superpower in science: patience. The universe will not hand you a clean answer just because a question feels important. The wow signal is almost 50 years old and remains a single event. Oumuamua is gone and cannot be reobserved. The cold spot is one sky feature in one universe. These are not laboratory conditions, they are detective work with missing pages. But here is the hopeful flip side. We are not stuck. We are building better tools. We are building radio arrays that will map the sky in unprecedented detail. We are building optical surveys that will catch fast transients routinely instead of occasionally. We are building telescopes that can measure spectra more precisely and search for subtle signatures of dust, gas, and magnetic fields. We are building statistical frameworks that can separate real structure from dot-connecting illusions. In other words, we are turning mysteries into programs. And that may be the real connection among all these strange discoveries. They are not proof that the universe is broken. They are proof that we are still early in the project of understanding it. A few centuries ago, we did not know what stars were. We did not know galaxies existed. We did not know the universe was expanding. Now we argue about giant arcs, ancient cold spots, interstellar vizinhs, and exotic explosions because our baseline knowledge has become good enough to notice what does not fit. That is progress, and it sets up the next part, because the most practical question is no longer why the universe is strange. The practical question is what happens next, what new instruments are coming online, what kinds of mysteries they are built to catch, and why the next few decades could be a golden age of weird. There is a rule in astronomy that is so reliable it almost feels like a law of nature. Build a better telescope and the universe will embarrass you. Not because you were foolish before, but because the cosmos is deeper than your instruments, and it always has more hiding just below your detection threshold. The moment you push that threshold down, you do not just see fainter versions of familiar things, you see new kinds of things, things nobody predicted, because prediction is limited by imagination, and imagination is limited by experience. This part is about that rule, the technological engine behind the modern flood of mysteries, and why the next wave is almost guaranteed to be stranger. Start with the simplest idea. Astronomy is not one science. It is many sciences stacked together, and each is defined by what you can detect. For most of human history, the only astronomy we had was naked eye astronomy. Points of light, patterns, motions, a sky that looked flat and fixed. Then Galileo pointed a telescope upward, and suddenly the sky was not flat. It had mountains on the moon, moons around Jupiter, phases of Venus. The cosmos gained depth in a single generation because a tool changed. That pattern never stopped. Radio astronomy opened in the 20th century and revealed a universe loud with invisible storms, pulsars ticking like cosmic clocks, galaxies with jets, and the afterglow of the Big Bang itself. X-ray astronomy revealed black holes feeding and hot gas in clusters. Infrared astronomy showed star formation hidden behind dust. Gamma-ray astronomy revealed bursts that can outshine entire galaxies for seconds. Gravitational wave astronomy revealed collisions of black holes and neutron stars through ripples in space-time. Each new window did the same thing. It did not just add detail, it revealed new phenomena. Now look at our list of mysteries through that lens, because it explains why they appear now. The WOW signal existed in 1977 because radio telescopes existed. Tabby star existed for as long as stars have existed, but it was discovered only after Kepler stared at one patch of sky with unprecedented precision for years. Odd radio circles were likely present in the radio sky all along, but they surfaced when survey instruments like ASCAP became sensitive enough to detect faint, extended structures. Oumuamua almost certainly was not the first interstellar object to pass through our solar system. It was the first one we caught because our surveys got wide and fast enough to notice. The cow and the fast blue optical transients are a perfect example of a new kind of blindness being removed. If an event peaks in a few days and fades in weeks, older surveys could miss it easily. The sky is large, telescope time is limited. If you are not looking at the right time, you see nothing. Modern time domain surveys change that. They watch large areas repeatedly, like a cosmic heartbeat monitor. That creates a new kind of astronomy that is not just about where things are, but about when things happen. So what changes next? A lot. One of the biggest drivers of the coming era is survey scale. Telescopes that do not just study individual objects, but map the sky in vast repeated sweeps. On the optical side, the Vera C. Rubin Observatory is designed to do exactly that. It will scan the sky repeatedly, building a movie of the universe that reveals moving objects, explosion, dimming stars and other transients on a scale that previous surveys could not match. It will not just find rare events, it will build statistics for them. It will let astronomers say not only that fast blue optical transients exist, but how often they happen, what galaxies they prefer, and what their full diversity looks like. On the radio side, the Square Kilometre Array is the monster tool on the horizon. When fully built, it is designed to have an enormous collecting area and sensitivity far beyond current arrays. That means fainter signals, larger maps, and deeper surveys. If odd radio circles are the first hint of a new category of faint radio structures, the Square Kilometre Array may turn that hint into a whole ecosystem. It may find many more rings, shells, relics, and unknown patterns. And if signals like the WOW event occur again, more sensitive radio surveys could catch them with a better localization and richer data, reducing the chance that a 72-second anomaly stays frozen forever. On the high-energy side, better monitoring means we catch more gamma-ray bursts, more tidal disruption events, more strange flares that could connect to exotic compact objects. On the exoplanet side, missions like the Transiting Exoplanet Survey Satellite and future space telescopes continue the work of finding worlds, but they also reveal stellar behavior we did not expect, because watching stars continuously is how you discover their weird habits. And this is where the weirdness becomes inevitable. When you build instruments optimized for one goal, you often get your biggest surprises as accidents. Kepler was built to find planets, it found Tabby's star. Surveys built to find near-Earth asteroids found Oumuamua. Programs built to catch normal supernovae found the cow. So we should expect the next generation of instruments to produce a similar pattern. They will succeed at their planned goals, and along the way they will reveal things that do not fit. The question is, what kinds of things? Here are some likely classes of future weirdness, not as predictions of specific objects, but as the kinds of blind spots we are actively shrinking. We will find more interstellar objects, and we will find them earlier. Earlier detection means better follow-up. It means spectra. It means better constraints on outgassing, composition, and shape. It means we may finally understand whether Oumuamua was a rare outlier or the first glimpse of a broader population. We will find more fast transients, including events that are even faster than the cow, maybe hours or minutes, which are almost invisible to slower surveys. Those could reveal new types of stellar death, new kinds of manetar activity, or entirely new explosive channels. We will map the cosmic web in finer detail at different epochs, testing claims like the giant arc and the big ring with larger datasets and better statistics. Some of those claimed structures may soften into chance alignments. Others may harden into real features that force adjustments in how we model structure growth. We will refine cosmic microwave background analysis and large-scale structure mapping, and we will better test anomalies like the cold spot. Maybe it becomes less anomalous with better understanding of the intervening large-scale structure. Maybe it remains stubborn. Either outcome teaches us something. We will study chemically peculiar stars with better spectroscopy and better models, perhaps turning Przybylski's star from an unsolved riddle into a case study in exotic atmospheric physics. Or perhaps it remains a thorn that pokes nuclear physics in ways we did not anticipate. And that is the emotional heart of this part. Science is not a march from mystery to certainty. It is a dance between what we can measure and what we can explain. New instruments widen the gap temporarily because they reveal things faster than theory can digest them. That is not failure. That is the normal rhythm of discovery. We are living in a time when astronomy is becoming more like a data-rich, always-on science. More eyes, more sky, more time, more wavelengths, more automation. And that combination is basically a machine for making anomalies, which brings us to the human side of the story. The people who stare at these anomalies. The emotional truth of how science feels from the inside when you are the one looking at the printout, the light curve, the spectral line, and realizing that something is wrong in the best possible way. Astronomy can look from the outside like a clean procession of facts. A telescope collects light, a computer turns it into numbers, a scientist turns the numbers into a conclusion. The universe is explained. Everyone goes home. Reality is messier and far more interesting. Most discoveries in this documentary did not arrive as a dramatic cinematic reveal. They arrived as a nagging mismatch, a number that was too high, a dip in a light curve that was too deep, a ring that looked too perfect, a point of light that moved on an orbit that did not belong. And the first response is almost never celebration. The first response is suspicion of yourself. Is the instrument wrong? Is the calibration off? Is the pipeline glitching? Is the background subtraction broken? Is this radio ring a processing artifact? Is this hold spot a map-making error? Is this spectrum line misidentified? Is this acceleration a mistake in the astrometry? If you want to understand science, you have to understand that the default emotion is not certainty. It is doubt, directed inward first. Jerry Amon wrote "wow" on a printout because the signal startled him. But before it became a legend, it was a piece of data that had to survive skepticism. It had to survive the uncomfortable question. Could this be interference? Could this be equipment? Could this be some ordinary signal that only looks extraordinary because we do not have enough context? The same pattern played out with Tabby's star. The first reaction to a 15% dip is not aliens. The first reaction is that something is broken. It is only after the data refuses to go away, after independent analyses confirm the dip is real, that the mind moves to the more interesting question. If it is not an error, then what is it? Odd radio circles started as circles on a map, which in astronomy is almost a synonym for suspicious. Circles are the shape of humans. We draw them, we make them, we see them. Nature does make spheres and shells, but the moment you see a perfect ring, you wonder if your software did it. The circles had to be confirmed by other telescopes to become real. The cold spot had to survive multiple satellite datasets. Oumuamua had to survive orbit fitting and reanalysis. The cow had to survive spectra, follow-up, and comparison to known supernova templates. This is what you do not always hear. Science is not the art of being right. It is the discipline of being hard to fool. And that discipline has a psychological cost because it means the most exciting moment in discovery is often paired with the most exhausting kind of uncertainty. You are holding a result that might be real, and if it is real, it matters, And if it is not real, you have just wasted months, and you may have published an embarrassment, and you may have built your own illusions, so you attack it. You try to destroy your own result. That is not self-hatred. That is quality control. When the result survives, something shifts. Skepticism becomes curiosity. Now the arguments begin, not about whether it is real, but about what it means. This is where outsiders sometimes misunderstand scientific disagreement. They think disagreement means the field is broken. They think if scientists argue, nobody knows anything. They treat debate as weakness. In reality, debate is the engine. When Tabby's star was at peak mystery, multiple explanations competed. Comet swarms, dust clouds, intrinsic stellar variability, alien megastructures as a provocative extreme. The debate was not chaos. It was a filtering process. Each hypothesis had to match the data, and each new observation could eliminate some possibilities while sharpening others. Oumuamua is the same. Outgassing, radiation pressure, fragmentation, exotic ice, thin sheet geometry. Every option is weighed not by how cool it sounds, but by how well it can explain the observed acceleration without creating contradictions elsewhere. The alien hypothesis gets attention because it is emotionally explosive, but in the real scientific conversation, it is treated as one possibility that carries a heavy penalty in assumptions. That penalty is important. It is called parsimony. The simplest explanation that fits the data is preferred, not because the universe is obligated to be simple, but because complicated explanations are easy to invent. If you allow unlimited assumptions, you can explain anything, which means you're explaining nothing. So scientists do a strange kind of balancing act. They keep their minds open enough to consider unusual ideas, but closed enough to reject stories that are not earned by evidence. That balance is not a personality trait. It is a skill, and it takes practice, and it sometimes creates tension between people who value different kinds of caution. Some scientists are conservative, preferring only explanations with close analogues to known phenomena. Others are more willing to entertain exotic possibilities, not as conclusions, but as prompts for new tests. Both roles can be useful because science needs brakes and it needs engines. Now step back and notice something even more human. These mysteries become famous not only because they are scientifically interesting, but because they trigger deep instincts in us. We are a species that hates unanswered questions. A one-time signal invites a story. A star that dims by 22% invites a story. A visitor from another star invites a story. We want closure. We want the final reveal. We want the villain or the mechanism or the explanation that makes our mental itch stop itching. But the universe does not care about our itch. The universe gives us partial data. The wow signal is one event. The cold spot is one region. Oumuamua is gone. Even the cow-like transients are hard because you catch them after the fact, and you reconstruct causes from light curves and spectra. Astronomy is the science of inference under brutal constraints, and that means some mysteries persist simply because we do not have enough observations yet. This is why the right emotional posture for science is not frustration. It is patience plus curiosity. There is a quiet dignity in admitting we do not know. In some belief systems, admitting ignorance is treated as weakness. In science, it is strength. It is the first step toward learning. Pretending to know is the real weakness, because it locks you into a story and stops you from gathering better data. The astronomers studying these phenomena are not embarrassed by uncertainty. They are motivated by it. The confusion becomes fuel. It drives new surveys, it drives instrument upgrades, it drives new models, it drives careful reanalysis of old datasets. Even when a mystery remains unsolved for decades, like the wow signal, the search for it improves our methods. It teaches us how to filter interference. It teaches us how to design better pipelines. It teaches us how to interpret narrowband signals and what false positives look like. The effort is not wasted. It becomes infrastructure. And that is the most important human story running underneath all the cosmic stories. We are not passively watching the universe. We are learning how to watch it better. So when you hear that Tabby star is still puzzling, or that odd radio circles are still being catalogued, or that the cold spot is still debated, it does not mean science is failing. It means science is doing its job in real time, out in the open, with the messiness left visible. And now we arrive at the final turn. All these strange discoveries, all these stubborn puzzles, all these debates and imperfect data sets, they lead to a single question that is both philosophical and practical. What is the universe trying to teach us through its anomalies? Is it telling us that our models are wrong in a fundamental way? Is it telling us that our models are right but incomplete? Or is it telling us something better, that the cosmos is simply larger than our current categories, and every generation will inherit new mysteries, because knowledge always has an edge?